Hi, I'm Paul Frisson, and I will present our work on quantum boomerang attacks and some applications. So first, I will talk about what boomerangs are, then how to turn boomerang distinguisher into key recovery attacks, then the quantum version of those attacks, whether it is the distinguisher or the last round attack, and then some applications. So what are boomerangs? Boomerangs are a technique first used by Wagner in 1999 to attack block cipher. To explain it, we will use two high probability differentials on the block cipher. So we have the first one going from alpha to beta with probability p over the first half of the block cipher, and then a second one going from gamma to delta with probability q over the second half. So the distinguisher goes like this. We start with two plain text with difference alpha, and then with the differential we know that with probability p we have a difference beta in the middle of the block cipher. So then we use the difference delta, and with probability q squared we get two differences gamma in the middle of the block cipher. Then, because we know three differences, we get the fourth one, which is another beta. And then with probability p, we get back a difference alpha between p3 and p4. So we made the distinguisher by taking p1 at random, computing the rest, and checking whether the difference between p3 and p4 is alpha or not. This distinguisher succeeds with probability pq squared because we use the differential twice. So how to make it into a key recovery attack? For that we will use an additional run on the block cipher. And on this additional run we will know the set of obtainable differences from delta through this additional run, and p out the probability of getting delta back from an element of define. And we will also assume that this additional run only involves a subkey of the whole key. So here is the situation. And the attack will contain three steps. The first one will be to get this event to happen. The second one will be to compute the subkey with the additional one, and then we will guess the rest of the key. So more formally, we follow those three steps, and for the first one, we generate a structure of ciphertext, such as any difference belongs to define. Then we compute the returning elements of the boomerang for every element of the structure, and we sort the structure by those returning elements. Then by looking at the sorted table, we can extract the pairs of ciphertext, such as the returning elements also have a difference in define. Then we get kout by computing all the possible kout, such as the incoming pair and the returning pair, leads to difference delta through the additional run and chaos. And we keep only the valid tuples that made a chaos that makes sense. Then we get the rest of the key by guessing it and checking if the whole key with chaos make a correct encryption. Then this attack succeeds with that complexity, and it is computed with the different steps of the attack. The first steps is mainly sorting the elements. This is why we get the size of the structure multiplied by the log of it. Then for getting chaos, we have the number of pairs multiplied by the cost of getting chaos for each of those pairs. Then we have the guessing part with the guessing of the rest of the key and the number of the pairs that we kept. So how does this translate into quantum? For that, we will use two main algorithms. The first one being the Grover search that will replace the exhaustive search in the classical setting. And it does so by a quadratic speedup. We will also use Ambeni's algorithm to search for collisions instead of the collision technique we used in the last round attack. So for the quantum distinguisher, here we have the Boomerang, and the only choice we have is taking the way we take P1, and in the classical setting we take P1 at random. In quantum we can do that by using the Grover search. So we will search for a P1 that has the right property. And this leads to that complexity. Then on the distinguisher we didn't have to do much, but for the last round attack the procedure was more complex, and so does the quantum version. So to remind the last round attack, there were 3 steps: getting this event to happen, computing chaos with the last round, and guessing the rest. So we followed those steps. We replace the collision search by Ambeni's algorithm. Then with the pairs, we search for a correct chaos. But clearly not every pair will lead to a chaos that makes sense. So we will search between the pairs for having only pairs that makes a correct chaos. Then we can search for the rest of the key, but not every pair leads to that. So we will need to search again for a correct pair, and then we will have a correct pair that leads to a good chaos and a good rest of the key, so we have the correct key. And this procedure succeeds with a near quadratic speedup of the classical one that I represented earlier. So for applications, we made two applications, the first one being on the Fireborn Cipher++. So there is a Boomerang attack on Cipher++ with time complexity of 2 to the 78. And then with our framework, we made a quantum equivalent that has time complexity of 2 to the 53.6. This is not a quadratic speedup, but this is explained with the fact that the main part of the quantum attack is the Ambénis search. And Ambénis algorithm is not a quadratic speedup, so this is why we cannot see a quadratic speed. And then there is also an attack on related key AES. So there is a Boomerang attack on the full AES in the related key model with time complexity 2 to the 99.5. And with our framework, we made an equivalent in the quantum version that has time complexity 2 to the 96.4. This time we are very far from a quantum speedup, and this is mainly due to the way the Boomerang is analyzed. And with more details, they use a particular analysis where when they get many times the same proposition for chaos, then the chaos is considered to be the correct one. And in quantum, this translates to some free distinctiveness, which is quite heavy in the quantum world. So to conclude, we propose the first efficient quantum Boomerang attacks with near quadratic speedup in theory, and we applied it on related KS and Cipher++. But on the attacks on practical ciphers, the quantum speedup was highly dependent of how the attacks were optimized, and this is why we made results that were not near the quadratic speedup that is the theoretical one. So thanks for watching.